Okay, so if you don't understand, don't bother, just let's go with the flow. Z10 is actually the set of all congruence classes modulo 10, which is what we will see it in the algebra videos that are going on. Okay, so in Z10, these two congruence classes turn out to be the same, although they look somewhat different. So there is a definition of equality, but the question is there any common properties that all the definitions of equality satisfy? Yes, there are some common properties that any concept of equality must satisfy, and we already know 3 of them. Together they are said to give us an equivalence relation, but there is a 4th one also. So let's just, in this context, in the context of this discussion, I'm going to write these properties. Okay, so the first property is, already know, reflexivity. If I have a concept of equality, then according to that concept, so to distinguish this from ordinary equality, like identity, two objects being the same, I am going to denote it, say, like this. Okay, so this is some definition of equality. Whatever it is, it must be reflexive, or it must satisfy the reflexivity property. What that means is this: A must be equal to A, modified equal to A, for every A, object A in the class C. This is reflexivity. Then we have symmetry. This also you know, you are familiar with this. If A and B are two objects in my class of objects C, and A is equal to B, then that implies B is equal to A. Then the third one is transitivity. So this one says that if I have 3 objects A, B and C in my class of objects, and I have A is equal to B and B is equal to C, then that implies A is equal to C. So whatever the definition of equality ultimately turns out to be in this class C, that has to satisfy these 3 things. Or in other words, I can express this by saying at once that this must be an equivalence relation on this class of objects. But there is one 4th property also that has to be satisfied. That is the axiom of substitution. Now this, however, its statement is somewhat large and a little unknown, although it's very natural, given to larger than these things, given to objects X and Y in C, if X is equal to Y, then Fx, oh, I am using this symbol, right? Then Fx is equal to Fy for any function or operation F. Okay, now note carefully. This X and Y are objects in the class C, right? If they turn out to be equal to each other according to the definition of equality in the class, then Fx must be equal to Fy. What is F? F is some operation or function in which if you put X as an input, then it gives some sort of output. Now this output is not necessarily a number or say something else. It can be anything. It is this Fx, Fy are some other objects of some other type. And this equality is yet another concept of equality in that class of objects, Fx, Fy. So since I already have used one symbol, so here I am just simply writing our ordinary equality symbol, but keep in mind that this Fx and Fy need not be numbers, they can be vectors also. So essentially what we are doing, this is a function or operation which takes us from this class C to yet another class of objects, and this must be true. Then only we can say that this is an equality, but this is not all. There is something else also here, and that thing is, it goes like this. Similarly, that is, this statement is not over. Similarly, if Px is a property pertaining to X, if X is say this class of objects is the class of all sets, then Fx can be cardinality of that set. Okay, if X is finite, if X is a finite set, then Fx may represent the cardinality of sets. In that case, this is definitely a number. Otherwise, Fx can be something else also. Say Fx can be the property, or Px can be the property that X is finite. Okay, so then Px does not have a value in the conventional sense, but it is a statement, okay, about X. So this is a property pertaining to X. Then, oh, I should not write then. And if X is equal to Y, then Px and Py are logically equivalent. Now, from our discussion of elementary mathematical logic, we now know very well what logically equivalent statements mean. They are either both true or both false. So here, if I put X, then I get a statement involving X. The similar statement I can make for Y also. These two have to be logically equivalent if these two objects turn out to be equal according to the definition of equality in this class C. So this is the axiom of substitution. Not only should our concept of equality satisfy the reflexivity, symmetry and transitivity properties, but it also has to satisfy the axiom of substitution, which involves any function or operation imaginable on the class of objects, also any sort of property that is imaginable, okay, which can be whose truth can be discerned without any ambiguity. Once you put some specific value of the object in this statement, that statement is either true or false. In other words, it's a well-defined statement. So these four things should be there in any concept of equality. Now let's come back to our definition of equality of sets. So we have already defined what sets, what their equality means. Now as we go along defining more and more axioms, you see what we are doing. We are defining the class of all sets, or rather we are trying to identify those collections of objects which belong to this class, that is, which are sets. In that class we have a concept of equality which is given by that definition of equality. Now we can prove these first three axioms, and in fact we are going to do that now, just like that, now itself. However, the axiom of substitution, as you can see, since f can be anything, any function or operation on sets, now our objects are sets, and p can be any statement involving sets. So as we introduce operations and statements on sets, we have to see whether the axiom of substitution continues to be true or not. It will be, but we have to keep that in mind. So now here, now this is not the thing. So here comes the first exercise of this section. Exercise 3.1.1. So what this exercise asks is this: show that the definition of equality in 3.1.4 is reflexive, symmetric, and transitive. Okay, so this is the first exercise, and its solution is very easy. It's obvious from the definition that for any two sets A and B, A is equal to A, and if A is equal to B, then B is equal to A. But let's just make sure why this obvious statement is obvious. To prove that A is equal to A, although it may sound silly, you have to look at the definition. Every element of A is also an element of A, and conversely. So that's why A is equal to A. It's obvious. So in that sense, it's obvious. And if A is equal to B, that means every element of A is an element of B, and conversely. But then by that, in the same vein, B is also equal to A. So that's why, hence, equality of sets is reflexive and symmetric. Transitivity, although it's also easy, it's not as obvious as this too. Next, for three sets A, B, and C, let A be equal to B and B be equal to C. Okay, then for any element A in A, we have A belongs to B, since it is given that A is equal to, or we have assumed that A is equal to B. So by the definition of equality, this any element of A must be an element of B. Also, B is equal to C, and so A belongs to B and so A belongs to B implies A belongs to C. Okay, so by the definition of this relation, we have this. Hence, every element of A is an element of C. One can similarly prove that every element of C is an element of A. Thus, A is equal to C. That is, equality of sets is transitive. Now, it may seem like too much ado about nothing, but we have to develop the habit of writing things properly, no matter how trivial it is, because then only when we go to the more difficult or more complicated parts of this theory or of any other parts of mathematics, there we will not make any mistake. So all our lines or whatever statements we write, every statement should have some solid justification. Okay, so that thing has to be kept in mind. Otherwise, the confusion will reign. So this ends the solution to this exercise. Okay, now here comes the first test for that axiom of substitution. Note that if x belongs to A and A is equal to B, then by the definition of equality we have x belongs to B. So this relation is an element of relation, which we also denote by this symbol, satisfies the axiom of substitution. Because x belongs to A is a statement. Remember, you can consider this as PA. Okay. Then the statement x belongs to B will be PB. Now, if A is equal to B, then PA and PB are both true. So, in that sense, the axiom of substitution has been satisfied by this relation. Now, the more relations and operations we define on the class of all sets, all of them must satisfy the axiom of substitution. Otherwise, we will have a problem with the definition of equality. because it will not satisfy the fourth axiom of equality, right? So here this relation has no problem. It creates no problem in the universe of sets. However, if we try to define, say, but note that we cannot define a notion of first element of a set, it will not satisfy the axiom of substitution. Let us see why. Okay, there is no, we cannot consistently define a notion of a first element in a set. Why? Because sets elements are not ordered in any, there is no natural order. We can write in whatever order the elements, if they can be written. We have already seen these things in naive set theory, right? In some sets the elements can be listed. They are small enough for that. But some sets are so large that we cannot list the elements. However, when we can list the elements, the order in which they appear, that is not relevant. If we try to define a first element in a set, because of that reason, this concept will not satisfy the axiom of substitution. Why? Because, for example, the first element, if we think of the first element, what we think of it, right? The first element of the set, say, let me take that set itself, 3, 4, 5, 9 is 3, whereas that of this set 4, 3, 5, 9 is 4. 4, 3, 5, 9 is 4. So these are different first elements. However, the sets are equal, because according to my definition of equality, they are equal. So my A is equal to B. However, if FA denotes the first element, then in the first case it is 3, in the second case it is 4. So axiom of substitution is not satisfied. So that's why the concept of a first element cannot be defined on the class of sets, unless we already have some sort of order, natural order defined on a set. Additionally, if we manufacture that thing, then we can define first element. So that's why the axiom of substitution should not be taken lightly. Okay, sometimes it may cause problems. So we have to, as we go to as we go further, we are going to check the axiom of substitution. Now, we also have to keep in mind that it's not the case that we have to always go on checking the axiom of substitution from scratch. The thing is that since this relation already satisfies the axiom of substitution, anything else that we define in terms of this belonging relation will automatically satisfy the axiom of substitution. So, provided that that thing is defined solely in terms of this. And most of the things in set theory are defined in terms of this. if we tweak this relation, we get some other concepts of some other sorts of entities like fuzzy set or things like that. Okay, but that is something entirely different. So this was the discussion involving the axiom of substitution. Okay, now we next turn to the, okay, so far we have seen only one axiom, right? Axiom 3.1, that sets are objects. But we have not as yet said anything about which collections are going to be sets. So we now turn to this issue. So we now come to the next axiom. So this is axiom 3.2. This is very easy. It's called the axiom of empty set. The axiom is just simply this, that there is an empty set. That's all. Or in other words, the empty set is actually a set. There exists a set consisting of no element. That is, if X is an object, or there exists a set, we can insert the symbol here itself. There exists a set which is denoted by this, consisting of no element. That is, if X is an object, then X is any object, then it is always true that X does not belong to this. Okay, we call this the empty set, or the null set or void set. Let me just write those things also for the sake of completeness. Or the null set or the void set. We sometimes denote the empty set by this symbol also, although it is less often used. Two curly brackets which enclose nothing. So it just denotes the fact that this set has nothing in it. Okay, but this is less often used. The more popular one is this Danish letter phi. Note one more thing, that I have said the empty set, right? There exists a set consisting, that is, we call phi the empty set. Now it can be proved, as we have already proved this in knife set theory, that if we consider two sets both having no elements, then they actually are equal. Okay, one can see from the definition of equality. Equality means equality of sets. Okay, from the definition of equality, that any two empty sets in the sense that both of them have no elements, that any two empty sets are equal. Okay, now the introduction of this empty set actually allows us to prove our first result, and that is, it's a very simple result, but it will become highly non-simple once we get to the axiom of choice. Lemma 316. This is 316, right? What was 315? 315. Oh, I forgot. Sorry. Extremely sorry about this. This is why the numbering should be kept intact. Before this, we have example. Actually, example comes before this, but anyway, before this axiom. Example 315. The content of this example is simple. It just shows two aspects of representing a set, or two aspects of sets that we already know. One thing is that in a set, the order in which the elements are appearing is not, it does not matter. So order is irrelevant. So we can write this set, or if I want, I can include one more element also. Like this, 1, 3, 5, 2. Then they are equal by the definition of equality of sets. So order of the elements in a set is irrelevant. One more thing is that we can, you already know this also, we can repeat elements. That will not change the set. Repetition of an element in a set does not further change the status of the element. What status? Whether it's an element in the set or not. Writing 3 2 times does not mean it's an element of this set more so than it was previously. So it does not change the set. It does not change the set. So that's just it. That's about this example 315. Now we can go to lemma 316. This lemma has a name, or it's given this name by Tao himself, I don't know. Single choice. It may sound obvious and stupid, but it will become, as I have said just now, it will become important when the size of the set becomes large, or when the sets become large. This involves only one set. We can have any finite number of sets or infinite number of sets. We'll understand that. Okay, let me just first write the statement. Let A be a non-empty set, then there exists an element or should I phrase it like this? There exists there exists an object. See, when we say object, we are not sure whether it is an element of the set or not. When we say element, it's already inside the set. So in that sense, we are using the words object and element. They have slightly different meaning when it comes to being inside a set or not. An object X such that X belongs to A. Okay. In this context, a non-empty set is a set that is not empty. We assume that this is already given, but ideally I should have defined it here itself. I mean, when we presented the second axiom that there exists an empty set, there itself we should have said that a set which is not equal to the empty set is said to be a non-empty set. Now, not equal to the empty set, that is available to me, that concept, because I already have the definition of equality. Okay, things should be kept straight. So with the assumption that I have defined this, so this is the lemma, which looks almost obvious, but nevertheless it needs a proof. Now, why are we being so emphatic about having proofs of trivial statements? It's because we are developing the theory from scratch. So anything we say must have a solid justification, and everything has to ultimately fall upon the axioms. So far we have only two axioms and one definition of equality. So based on those things only we have to prove this. Okay, you cannot say this is obvious to me, so that's why it's true. Many things in mathematics seem obvious, but often they turn out to be not true. Okay, so to prove this, we approach by contradiction. Then there exists an object.